In this lecture, we will talk about chi-square test, which is discussed in chapter 10 of Kothari book, second edition. And I have prepared some notes for it. So let us first see what is chi-square distribution. Now, let us say x1 is a standard normally distributed random variable. So what that means is the distribution of x1 is something like this, what you see here, the bell curve. It's a normal distribution. The mean is 0 and the variance is 1. So we generally write it like this, x1 n. That means it's a normal distribution and mean is 0, variance is 1. So it is a standard normally distributed random variable. Okay. If we define a new random variable q1, which is just x1 square, so just like x1 is a random variable, q1, which is x1 square, is a random variable, and the distribution of q1 is going to be something like this, what you see here. Q1 cannot be negative because it is just square of a number, and the distribution will be like this because you see x1, the distribution of x1 has a peak around 0. So that's why if you're taking x1 square, it will also have a peak around 0, and then q1 is just positive, what you see here. Okay. So this q1, the distribution of q1, what you see here, this is an example of a chi-square distribution. And this particular chi-square distribution, it has 1 degree of freedom because you have here only one variable here, this x1. Okay, so it is chi-square distribution with 1 degree of freedom. Now similarly, let us say uh, we have a variable x1, random variable, which is normally distributed, and also another variable x2, which is also normally distributed just like x1. And say both of these, x1 and x2, both of these are independent. Now we can define another variable q2 as x1 square plus x2 square. Okay, so and if we look at the distribution of q2, it will be something like this. It will still have a peak around 0. Okay, nothing on the negative side, it will always be positive, and the tail will be like this. Okay, so this is called a chi-square distribution with 2 degree of freedom. Okay, similarly, we can have a chi-square distribution with 3 degree of freedom, 4 degree of freedom. Let us look at 3 degree of freedom also. Now we have x1, which is normally distributed. It's a standard normal distribution. X2 also standard normal distribution, and x3 also like that. And we define q3 as x1 square plus x2 square plus x3 square. And we now this q3, if we plot a distribution of that, it will look something like this. Now we see the peak is not around 0, and the reason for that is obvious because uh, to get a 0 for q3, all x1, x2 and x3 have to be 0 simultaneously. Okay, so even if one of them is non-zero, we will not get a 0 q3. So that is why the distribution does not show a peak around 0, rather peak occurs later, and then it has a long tail. So this is called chi-square distribution with 3 degree of freedom. Okay, in the same way we can define, let us say qk. It is just sum of k such terms, sigma xi square. So that is x1 square plus x2 square up to xk square. Each of these x1, x2, x3 are standard normally distributed, and they are independent. Okay, then we'll call this qk, it will have a chi-square distribution with k degree of freedom. Okay, So that's what a chi-square distribution is. And let us look at a comparative figure in the book. So this figure 10.1, and here you can see how chi-square distribution looks like for different degrees of freedom. If degree of freedom is 1, it looks like this. And then here it is shown for some degrees of freedom. For 3, it will be like this. And as degree of freedom increases, the peak occurs later. Okay, and the higher values are also more likely. So that is why you see that if degree of freedom is just 1, it drops to very low value. The distribution drops to low values quickly. But if degree of freedom is high, let us say 10, which is actually a sum of 10 terms, so you are likely to have higher values also, and the distribution is like this. Okay, so that is chi-square distribution. Now, while using chi-square distribution, we will always encounter this type of calculation, as you see here. So this is, say, a chi-square distribution with 3 degree of freedom, and we will need to look at some values from the table, okay, which is table 3 in the appendix. And as an example, let us say we have to find the value here for which uh, the area to the left of so this is the value of chi-square, for which the area to the left is 90% and to the right is only 10%. So what will be this value of chi-square uh, uh, for 3 degree of freedom chi-square distribution? Okay, we are going to get that number from table 3. So let us see how to get that. Because in table 3, you see it gives critical values of chi-square, and the first column is degree of freedom, and then it gives you this 0.99, 0.95, 0.50, which is related to the area. Okay, so now say we have degree of freedom 3, and we want the critical value of chi-square for which the area to the right is 10%. Okay, area to the right is 10%. Okay, so you see that in the table, degree of freedom is 3 and area to the right is 10%. That means this 0.1, and corresponding to this you can read the chi-square value 6.251. Okay, so let us take another example. Say degree of freedom is 9, and we want the critical chi-square value for which area to the right is let us say 5%. Okay, and degree of freedom is 9. So if degree of freedom is 9, we see degree of freedom 9 here, and area to the right is only 5%, so that is 5%. So the critical value of chi-square will be 16.919. Okay, so that is how we read from this table. Okay, now what is the use of chi-square test? It is used in different situations, and uh, basically 3 situations we are going to discuss and some examples of each situation. One is chi-square test for comparing variance. Okay, chi-square test for comparing variance. Uh, I'm just doing this example, which is illustration 2 in the textbook. And the question is, a sample of 10 is drawn randomly from a population. Okay, so our sample size n is 10, and the sum of squared deviation from mean is 50. Okay, sum of squared deviation from mean is 50. So what that means is basically this term sigma xi minus x bar. X bar is the mean of the sample, and xi minus x bar, this is deviation from the mean. Okay, we are squaring it and adding. So that is what is meant by the sum of squared deviation from mean. So okay, that is given as 50. Now we have to test the hypothesis that the variance of the population is 5. Okay, at and we are given 5% significance level. So this is the question. So this will come in the category of comparing variance, because we are actually looking if our sample is from a population which has a variance of 5. Okay. So the null hypothesis will be that the variance of the population, variance is actually the square of standard deviation. The null hypothesis is that the variance of the population is 5, and alternative hypothesis is that the variance is not equal to 5. Okay, and we have to do a chi-square test here. So depending on the test, and we have a sample, so we have some data from the sample. We always work out a test statistic. We have discussed it previously that statistic is something we obtain from the sample, and the parameter is something which we obtain from the population. Okay, so the parameter is a characteristic of the population, and statistic is a characteristic of the sample. So in this case, we are working out chi-square statistic, what is called chi-square statistic. And chi-square is defined as we discussed just previously, that it is like x1 square plus x2 square plus x3 square. That is how chi-square is defined. So in this case, that takes this form, that chi-square definition, that takes this form, sigma s square. Okay, this is sigma s square. This is variance of the sample times n minus 1 divided by variance of the population. Okay, this is how chi-square is defined. And if you look at this term, say this sigma s square times n minus 1, that is just going to be this term, sigma xi minus x bar square. Okay, that is going to be just this term, and divided by sigma p square. So it is just summation of terms. And if you look at it carefully, you will see that it is actually summation of terms, uh, each of which has a standard normal distribution. Okay, so now we just put numbers here and we get this chi-square statistic. Now the sigma s square, that will be the sum of squares, square this deviation, this 50, divided by n minus 1. N minus 1 is here is 9. So this is the variance of the sample, multiply by n minus 1, which is 9, divide by the variance of the population, which we took as 5. So we get the test statistic as 10. Okay, and the degree of freedom here is equal to n minus 1. N is sample size, degree of freedom is n minus 1, which will be 9. And we have discussed this previously, that the degree of freedom here is not 10, it is 9, because out of 10 pieces of information, that is say x1, x2, x3 up to x10, if you know 9, x1 to x9, then x10 you know automatically, because you have information about the mean. Okay, so the degree of freedom is 9, n minus 1. Okay, so then say we have this chi-square distribution with degree of freedom 9, and we will have to read the critical value of chi-square from the table, from table 3. We are going to read the critical value of chi-square uh, at 5% significance level. Okay, 5% significance level means that the critical value of chi-square, for which the area to the right is 5%, and degree of freedom is 9. Okay, so let us go to that table, table 3. So we have degree of freedom 9, and for 5% that will be 0.05. So critical value of chi-square is 16.91. Okay, that's all we have to read from the table. So you have here the critical value of chi-square is 16.92, and to the right of this we have the rejection region. okay, in which we will reject null hypothesis, and to the left is the acceptance region. And now we see the chi-square test statistic that we worked out. Its value was 10. So 10 lies in the acceptance region. So our result is going to be, we will accept the null hypothesis. Okay, at 5% significance level, we have accepted the null hypothesis, which was that the sample is from a population with variance 5. Okay, so this is the types of problem we deal with when we are using chi-square test for test of variance. Let us look at another example of this, which is illustration 1 in the textbook. Okay, see this illustration 1, this chapter 10. Okay, it says weight of 10 students is as follows. Uh, so the weight of 10 students are given here. So effectively we have a sample with sample size 10, and the question says, can we say that the variance of the distribution of weight of all students from which the above sample of 10 students was drawn is equal to 20 kilogram? Okay, so again the question is that, can we say that the variance of the population is 20? And it says test this at 5% and at 1% level of significance. Okay, so we have to use the chi-square test, and in this case, see, you can, if you like, you can construct a table like this. You are given a sample of size 10, so x1 to x10. First you work out the mean x bar, which is sigma xi over n, turns out to be 47 here. Then you work out the deviation xi minus x bar, okay, the square of deviation and sum of squares of deviation. It turns out to be 280 here. We can work out the standard deviation of the sample, which is defined like this, you already know, square root of sum of square deviation over n minus 1. It turns out to be this. Okay. Our null hypothesis is that sigma p square is, what was the value in the question? Sigma p square is 20. Okay, that will be the null hypothesis, and we work out chi-square statistic, which is defined like this in this case. We just plug numbers here for sigma s square, sigma p square, and n minus 1. It turns out to be 13.99. Now we need to read the critical value of chi-square. The degree of freedom here is n minus 1, 10 minus 1, that is 9. And at 5% level of significance, you get the critical value of chi-square as 16.92. And at 1% level of significance, again from the same table, table 3, you get the critical value is 21.67. And if you look at our statistic, 13.99, for both it lies in the acceptance region. So we just accept the null hypothesis. That is the conclusion. Okay, so that is how the chi-square test is applied for test of variance. Another situation where chi-square test is used is for goodness of fit. Okay, which basically means to see how well the assumed theoretical distribution fits the observation. Okay, so let us understand this with one example, just a very simple example. Say a coin is tossed 50 times and we get 20 heads. Okay, and now the question is the coin biased? Okay, it is biased or it is not biased, and we have to answer at 5% significance level by using chi-square test. Okay, now we define null hypothesis as the coin is unbiased. Okay, And when we say the coin is unbiased, now this is our theoretical, uh, this will give us a theoretical distribution which we can call the expected frequencies. Okay, what that means is if the coin is unbiased and we are tossing the coin 50 times, then we are going to get 25 heads and 25 tails. Okay, so that is what is meant by the expected frequency. So if you see here, we are seeing how well the assumed theoretical distribution fits the observation. Okay, observation in this case is, see, observed frequency in this case is head is 20 and tail is 30. Okay, that is observed frequency. And along with that, we can also write expected frequency, which is based on what we are assuming. Okay, our null hypothesis is that coin is unbiased. If we, based on that, we get our expectation is 25 head and 25 tail. Okay, so that is the first step in this. You work out the expected frequency based on the null hypothesis. Okay. Okay, then we work out the test statistic, chi-square statistic in this case, and that is defined as summation of observed frequency minus expected frequency, square of that divided by expected frequency. Okay, summation of all these terms. Uh, so in this case, we have two categories. We have head and tail. Okay, just two categories. So summation over these two, which will become, for head, our observed frequency is 20, expected is 25. So this term will become 20 minus 25 square divided by expected is 25, 25. Okay, plus for the second category tail, same thing, observed is 30, expected is 25. So 30 minus 25 square of that divided by 25. Okay, so we get chi-square, our test statistic of 2. Okay, and now the degree of freedom here is n minus 1, uh, which is 1. Okay, n is number of categories here. We have two categories, head and tail. So if you say the coin is tossed 50 times and head we got 20 times, okay, then we automatically know that the tail is 30. So there is only one piece of information uh, which we need to know. So the degree of freedom will be 2 minus 1, 1 in this case. Okay, so we have worked out our chi-square statistic and degree of freedom. And now from the table, from table 3, we'll have to read critical chi-square value for 1 degree of freedom at 5% significance level. Let us see that. Okay, so for 1 degree of freedom at 5% significance level, critical chi-square value is 3.841. Okay. See, the critical chi-square value is 3.841, and the chi-square statistic we got is 2, which is less than the critical value, so it will fall in the acceptance region. So we just accept the null hypothesis. Okay, and the null hypothesis was that the coin is unbiased. Okay, so this is an example of goodness of fit, uh, in which we see if our observation fits the expectation of distribution based on some theory that we have. There are many examples of this in our book, particularly example 3, 4, 5, and 8 in 10th chapter. So let us just go through these quickly. Okay, here you see example 3. It says a die is thrown 132 times with the following result. Okay, 1 turned up 16 times, 2 came 20 times. So like that, the frequency is given. Okay, just like the tossing of coins, in this case, we are throwing a die 132 times and the frequencies are given. If you add all of these frequencies, you will get 132. And the question is the die unbiased? Okay. So we have here, uh, you can make a table like this, number turned up from 1 to 6. So we have six categories here. Instead of head and tail in the previous example, we have six categories. Observed frequency, this is from the experiment that is given. And now expected frequency, if we assume that the die is unbiased. Okay, if the die is unbiased, then the expected will be, for each will be 132 divided by 6. Okay, we're throwing it 132 times, divide that by 6, that will be the expected frequency for each of these. So we have observed frequency, expected frequency. We can do observed minus expected, and observed minus expected square of that, divide each of these by the respective expected frequency, and then add these. That will give us the chi-square statistic. Okay, that is done here. Sigma O minus E square over E. It turns out to be 9. And now the degree of freedom here is 6 minus 1, 5. We have 5 degree of freedom. And significance level in the question is, actually it is not specified. So let us say it is 5%. What they have taken is, they have taken 5%. Okay. For degree of freedom 5 and a significance level of 5%, we can read value from the table. The critical chi-square value, that turns out to be 11.07. But our chi-square statistic is 9. It falls in the acceptance region. Okay, so the conclusion is that we say that null hypothesis is accepted, so the die is unbiased. Okay. Let us look at example 4. Uh, it says find the value of chi-square for the following information. Okay, we are given these classes or categories A, B, C, D, E. Observed frequency is given, and theoretical or expected frequency, okay, by whatever assumption they have calculated, that is this, we have to just calculate the chi-square value. Okay, so generally we do observed minus expected, square of that divided by expected, and add them. But here one thing we have to note is, see here it says some of the frequencies are less than 10. So if you look at the like here, the frequency is 8, and frequency here is 4. Now whenever the frequency is less than 5, or even if it is less than 10, then the formula we use for working out the chi-square, see this formula here, in this formula there is an assumption of standard normal distribution, and that assumption is not valid. Okay, if the frequencies are very low, say less than 10. So what we have to do is we have to do some grouping of categories or classes. So in the solution you can see that class A and B, they have been grouped together. Okay, because here frequency was less, 8. So now if we group them together, then observed frequency becomes, for A and B together, it becomes 37. Okay, observed frequency is 37, and expected also you add 7 plus 24. Okay, that is the expected frequency. Okay, now the C is fine. Now for E also frequency is low, so we can group D and E together. So that is what you see here, D and E are grouped together. So their observed frequencies are added, expected frequencies are added. And then based on this, we do the same calculation and work out chi-square. Okay, that is the only difference if class frequencies are low. Okay. Let us look at another example, illustration 5. It says the genetic theory states that children having one parent of type A sorry, one parent of blood type A and the other of blood type B will always be one of the three types A, B, or AB, and that the proportion of three types will be on average P1 is to 2 is to 1. Okay, so it is giving us a theory that uh, if one parent is A, blood type A, other parent is blood type B, then there are three possibilities for the child, that the child will have blood type A, B, or AB, and the proportion is given 1 is to 2 is to 1. Okay, that is the theory. A report states that out of 300 children having one A parent and one B parent, 30% were found to be type A. That means 30% of 300, that is 90. Okay, 90 were found to be A, 45% type AB, and remainder type B. Okay, so we know the frequency of A, AB, and B. We know the frequency from the data, and we also know the expected frequency from the theory. Okay, theory says 1 is to 2 is to 1. That means 25% will be A, 50% will be AB, and 25% will be B. Okay, so we have the observed frequency and the expected frequency. Okay, and it says test the hypothesis by chi-square test. Okay, so our null hypothesis will be that this theory of 1 is to 2 is to 1, this is right. That will be our null hypothesis, and alternative hypothesis that it's not right. Okay, and we are just seeing that our observation fits this theory or not. Okay, so this is goodness of fit test. And we can make a table like this. So we have type A, B, B. So these are the categories, three categories. Observed frequency, uh, it is given. Expected frequency based on 1 is to 2 is to 1, that is given. Okay, so we can work out the chi-square statistic as previously. It turns out to be this. Degree of freedom, here will be 3 minus 1, 2. At 5% level of significance, we read critical chi-square value from the table turns out to be 5.99, and our statistic value is 4.5. So it falls in the acceptance region. Okay, so we say the theory, this 1 is to 2 is to 1 is right. We just accept the theory. Okay, so again, goodness of fit. And let us see, there is one more example, I think number 8. Okay. This question says 8 coins were tossed 256 times. Okay, so each toss had 8 coins, and and the following results were obtained. Number of heads. Okay, 0 head, we got 2 times, 1 head 6 times, up to 8 heads 1 time. And the question is, are the coins biased? Okay, so we are given the frequencies from the experiment, and as we did in the previous examples also, first we need to work out the expected frequencies. Okay, and based on our hypothesis, the hypothesis will be that the coin is unbiased. Okay, if the coin is unbiased, we can work out the expected frequency for 0 heads, 1 head, like that. Okay, so which is worked out in this table. So for 0 head, it will be 8C0 because each toss has 8 coins in it. So out of 8, all were 8C0. You will write it like this. Then the probability of head is half, and probability of tail is also half. So half to the power 0, half to the power 8. And because we want expected frequencies, we will multiply it by the number of experiments we did. So there were 256 experiments. Okay, so this gives us the expected frequency for 0 head. Okay, so like that, for 2 heads we will do 8C2, because from from the 8 coins, any two could have been head. So 8C2, then probability of head is half square because two heads, then tail is half probability to the power 6 because we got six tails. If we have two heads, we'll have six tails. And then to get expected frequency, we multiply it with the number of experiments. Okay, 256. So we get the expected frequency. Okay, so like that, we work out the expected frequencies and then we do the same thing. Okay, these are our categories. We have observed frequency, expected frequency, and we work out the chi-square statistic, and then we read the critical chi-square value for degree of freedom 8 in this case, and see if we accept or reject the null hypothesis. Okay, so these were examples of goodness of fit. Another situation where chi-square test is used is for test of independence. Okay, and in test of independence, it basically enables us to explain whether two attributes are associated or not. Okay, we'll see what it means through one example, which is illustration 6 in the book. The question here is, a situation is given, uh, uh, the data for the situation is given here, and it is asked, is vaccination effective? Okay. And we have to test at 5% significance level using chi-square test. Okay, so the data here is for 2000 people. What you see here, for there were a total of 2000 people, and out of 2000, 500 were vaccinated. They were given some vaccine. So you see, vaccinated total is 500. Okay, out of 2000, 500 were vaccinated, and 1500 remaining were not vaccinated. And then it was seen whether they were attacked by by the particular disease or not. So out of 500 which were vaccinated, the data that is collected is 469 were not attacked and 31 were attacked. Okay. And out of 1500 which were not vaccinated, 1315 were not attacked and 185 were attacked. Okay. So then the total attacked turns out to be 216. We just add these, that is the total which were attacked, and the total not attacked turns out to be this. Because the idea here is simple, uh, that from in a group of 2000 people, some are given vaccine, some are not given vaccine, and then it is seen that how much from the vaccinated category they were attacked, and how much from the not vaccinated category they were attacked. And based on that, we have to see if the vaccination is effective or not. Okay, so this will come in the category of test of independence. Okay, uh, independence in the sense that if we say that vaccine is not effective, okay, if we say vaccine is not effective, that means we are saying that vaccination and attack by the disease, they are independent. Okay, it does not matter if you are vaccinated or not vaccinated. They are independent things, because vaccination is not affecting uh, the attack. Okay, so when we say the vaccine is not effective, we are saying that vaccination and attack are independent things. They are not related, they are not associated. If we look at the data here, if we just calculate the percentage, if we do this 469 by 500, so it turns out to be 93.8%, and 1315 by 1500 turns out to be 87.6%. So by looking at the numbers, if you we can see that 93%, around 94% of the vaccinated people were not attacked, whereas only 87% of the not vaccinated people were not attacked. So it looks like the vaccine is somewhat effective. uh, but we need to do the chi-square test, okay, at 5% significance of level for our conclusion. Now the null hypothesis will be that the vaccination is not effective, which means, as I already explained, that there is no association between vaccination and attack. Okay. And as we did in the previous examples of goodness of fit, we have a null hypothesis, and based on that, we work out the expected frequencies. We are going to do the same thing here. See, all of these are frequencies: 31, 469, 185, 1315. These are frequencies that were observed. And now we are going to work out the expected frequencies based on the assumption that vaccination and attack are independent. Okay. And for that, we use the simple idea of probability. Probability of A and B is written as probability of A multiplied by probability of B if A and B are independent. Okay, very simple result of probability we use many times. So now, see, to fill the expected frequency here, uh, because the number that will go here for the expected frequency will be the number, the expected frequency for vaccination and attack. Okay, vaccination and attack. Okay, so I've written here probability of vaccinated and attacked. Okay, that will be probability of vaccinated and probability of attacked, multiplication of these, because we are assuming that these are independent. And probability of vaccinated will be, you see, 500 people were vaccinated out of a total of 2000. So 500 divided by 2000, that is the probability for vaccinated. And probability for attacked will be 216 were attacked out of 2000. So 216 divided by 2000. Okay, so 500 by 2000 multiplied by 216 by 2000, this is probability. But we don't want probability, we want expected frequency. So the frequency of vaccinated and attacked will be, we just multiply this with the total number 2000. Okay, so this will give us the expected frequency. This number turns out to be 54. And here we have made an expected frequency table. This number you see is 54. Okay, so just like this one, we need to work out the expected frequency for other three, uh, uh, these other three expected frequencies also. And you can do that very quickly, because see, the result here becomes to get the expected frequency. It turns out that what you have to do is, to get expected frequency, for example, here corresponding to 469, what you do is you multiply this 500, okay, this row total and column total, multiply 500 and 1784, and divide it by the total, that will be 2000. Okay, so you'll get the expected frequency for this one, which turns out to be 446. Okay, similarly, to get expected frequency corresponding to this value 1315, we multiply the row total 1500 and the column total 1784, and divide this with total, that is 2000. Okay, so you will get 1338. Okay, so like that. So now we have observed frequencies and expected frequencies. So we can calculate the chi-square statistic. Chi-square statistic is the summation observed minus expected square over expected, and we have four values here. It was a 2 by 2 table. Okay, so observed minus expected square over expected, just add those things and we get chi-square statistic for 14.64 here. Okay, now we have to also look at the degree of freedom, and now degree of freedom here will be number of rows minus 1 multiplied by number of column minus 1. So becomes 2 minus 1 times 2 minus 1. It just becomes 1. Okay, and the reason for this is the following, you see. Uh, so if we are given this information, let us say 2000 people, uh, let us go to this table. We are given a total of 2000 people, 1500 were not vaccinated, 500 were vaccinated, and it turned out that 216 were attacked and 1784 were not attacked. Okay, then in this table, you see there is only one piece of information that we need to know. If we know that 31 were attacked, then we automatically know 469 were not attacked, because the total of these have to be 500. So we just need this information. We don't need this. And if we know 31 were at, 31 will be the number here, and the total here is 216, then we automatically know it is going to be 185 here. Okay, so that is why it becomes number of rows minus 1 multiplied by number of column minus 1. That degree of freedom is that. Okay, so degree of freedom is 1, and chi square is 14.64. And now from the table, okay, you can see for degree of freedom 1, significance level 5%, critical chi square value is 3.841. The critical is 3.84, our value is 14.64, so it falls in the rejection region. Okay, because chi square is greater than the critical value, so we'll reject H0 and conclude that the vaccine is effective. Okay, now finally one more point. So see, we discussed what is chi square distribution, and the degree of freedom for that, and the table that we use to read the critical value of chi square, and three scenarios in which chi square test is used. One is for the test of variance, other is for test of goodness of fit, in which case we work out the expected frequencies first and then do it, and other is uh, for test of independence. Okay, in which case we assume, we take the null hypothesis as that the there is no association or there is independence, and we work out the expected frequencies based on that, and then do the same thing. But just be careful that the degree of freedom, the way the degree of freedom is determined in that case. One final point here is the additive nature of chi square, uh, which is, there is a formal proof of that. We don't need to get into that. Uh, but basically, what it means is that the several values of chi square can be added along with adding their degree of freedom. Okay, this gives degree of freedom of total chi square. Okay, so let us say x1 and x2, these are independent independent variates, and they both follow chi-square distribution. Okay, so x1, that it has a chi-square distribution and degree of freedom is n1, and x2 also has a chi-square distribution, degree of freedom is n2. Now if we add x1 and x2, so x1 plus x2, the result will be a chi-square distribution only, and the degree of freedom of this chi-square distribution will be n1 plus n2. So we are just adding the degrees of freedom uh, as we are adding the chi-square values. Okay, and this idea is useful many times. We'll look example 10 from the textbook where this idea is used. Okay, so in example 10 it says the following values of chi-square from different investigations carried to examine the effectiveness of a recently invented medicine for checking malaria are obtained. Okay, so there may be just one investigation. Say they have give numbered it investigation one. Okay, there was some sample size uh, um, for the investigation, and they have determined that chi-square value for that was 2.5, and degree of freedom for this investigation was just 1. Okay, and they have also done another investigation, so like that 5 different investigations have been done. Okay, there is a chi-square value and degree of freedom associated with each. Now, see, one thing is to conclude based on just one investigation, but the conclusion will be better uh, if all investigations are taken into account. And that can be done here very easily because of additive property of chi-square. Okay, so we can add all these chi-square values and you get the total is 18. Okay, if you add the total is 18, we can also add all these degrees of freedom and we get degree of freedom is 5. Okay, so effectively you can say that our observation is that we got a chi-square of 18 and our degree of freedom is 5. Okay, so we have taken all investigations into account and our conclusion will be based on that. Okay, now for if the degree of freedom is 5 and if let us say the significance level is 5%, then critical chi-square value from the table is 11.07. Okay, but our statistic is 18, so which falls in the rejection region. Okay, in the rejection region, so we reject the null hypothesis. Null hypothesis was basically that the new medicine is not effective. Okay, so the conclusion will be that the medicine is effective. Okay, so that is how the additive property of chi-square is useful.